Hi everyone. In this video, we're going to introduce the concept of hyperbolic functions. To motivate the idea of hyperbolic functions, let's think about some things that we learned recently. In particular, we learned that it can be useful to look for sums and differences of squares when finding antiderivatives, since it can suggest making use of an inverse trig formula such as arcsine or arctan or arcsecant. But you might notice the formulas we've come up with so far are somewhat limiting because, for example, the arcsine formula requires that we have a difference of squares under our square root. But what if we had a sum of squares instead? Or what if we had a difference of squares of the form u squared minus a squared rather than a squared minus u squared? Well, we don't currently actually have a way to deal with these situations, but it kind of feels like we should have a way since these are really similar to integrals that we do know how to handle. Essentially, to answer those types of integrals, we would need to have something that behaves like an inverse trig function, but maybe isn't actually an inverse trig function. And it turns out there is such a thing. They're called inverse hyperbolic functions, and that's what leads us to the topic of this video. So let's start with the basic definitions. There's a certain function that we call hyperbolic cosine, and we refer to that function as cosh of t. Very much how the traditional cosine function might be called cosine of t or cos of t. You might also hear others pronounce this function as cosh t, but I prefer to call it cosh t. But what actually is cosh of t? Well, it's defined as this function, e to the t plus e to the minus t all over 2. Currently, that probably looks like a very random definition, but as you learn more about this, you'll see that this is actually quite a useful function. Similarly, we have a hyperbolic sine function. I pronounce this one sinh of t, though others may pronounce it shine of t. And this function is identical to cosh of t, except that we subtract instead of adding in the numerator. There's also a hyperbolic tangent, which is usually pronounced tanch of t, and that's defined exactly how you would expect. If tan is sine over cos, then tanch should be sinh over cosh. That being the case, a formula for tanch of t can be obtained just by dividing the formulas for sinh and cosh respectively. So you can pause and check these details of that formula if necessary. These definitions are the ones we use whenever we need to calculate the value of a hyperbolic function, so make sure to write these down on your formula sheet. A curious thing about hyperbolic functions is that they're named after trig functions, sine, cosine, and tangent. And the reason for that is because hyperbolic functions behave a lot like trig functions, as it turns out. So let's explore this connection a bit further. Here's a fact that we know about trig functions. Cos squared plus sine squared is always equal to 1. That's an identity you should already know from high school. But it turns out it's also true that cosh squared minus sinh squared is also always equal to 1, a fact which is extremely similar but ever so slightly different to what we already know about trig functions. But how do I know that what I just said is actually true? Let's prove it. To start with, let's consider this quantity, cosh squared minus sinh squared, and we're going to show that it really is equal to 1. To do that, we can make use of the definition of what cosh and sinh are in the first place. So here I've just plugged in our formula for cosh of t, and similarly, I can also plug in our formula for sinh of t. All that remains now is to simplify and check that we really do get a result of 1. So let's expand all of this out and see what happens. First, notice that on the denominator, 2 to the power of 2 can become 4. And in the numerator, to apply the power of 2, we need to FOIL everything out, providing us with the result that you see now. You can pause and check that if necessary. Now, this is just our first term. But our second term can be expanded out in a very similar fashion, so again, pause and check if needed. And at this point, notice that both our terms have a common denominator of 4, so we can directly subtract the terms in the numerator. After subtracting, we'll see that e to the t squared cancels with minus e to the t squared. And the same observation can be made with e to the minus t squared. With the remaining terms, we see that we are subtracting a negative, and that means the remaining terms will add together to give us the result that you see now. Pause and check that if necessary, and next, if we cancel these 4's, we're left just with e to the t times e to the minus t, but using exponent laws, that simplifies to e to the 0, which has a value of 1, and that completes our proof. So hopefully this gives you at least a vague sense of why hyperbolic functions are named after trig functions. But why do we call them hyperbolic? Where does that word come from? Well, the reason for that again has to do with this trig identity. So let's take this identity, and let's say cos of t and sine of t get represented as x and y respectively. If we do that, then our identity becomes the equation x squared plus y squared equals 1. And you should recognize this equation. It's the equation of the unit circle. Now, what this means is that cos and sine respectively designate the x and y coordinates of all the points on the unit circle. And that's something that you already know from high school, but let's see if we can apply the same type of thinking to hyperbolic functions. So let's take this identity, which we now know is true, and in similar fashion, let's say cosh of t and sinh of t get represented by x and y respectively. If we do that, we get the equation x squared minus y squared equals 1. Now that equation would be less familiar to you, but it's commonly known as the unit hyperbola. The graph looks like this, which you can check for yourself. And the shape of this graph is characteristic of what hyperbolas look like in general. But the point being made is that cosh and sinh designate the x and y values on the unit hyperbola, just as cos and sine designate the x and y values of the unit circle. And that's the reason we call these functions hyperbolic, in case you were wondering where that name comes from. Now, if we have hyperbolic sine, cosine, and tangent, it would make sense if we also had secant, cosecant, and cotangent. Let's think about hyperbolic secant, which is commonly pronounced as sech of t. The definition is exactly what you would expect. Secant is 1 over cosine, and we already have a hyperbolic cosine, so this makes sense in light of the definitions that we already know. In similar spirit, you can define hyperbolic cosecant, which you might call cosech, and also hyperbolic cotangent, which you might call cotang. Now, just as we know a bunch of trig identities from high school, it turns out there are also a whole bunch of hyperbolic identities, which are very similar to trig identities. And these are just statements of equality, which are always true. So for starters, we know that cosh squared minus sinh squared is always equal to 1 for all values of t, so this is an example of a hyperbolic identity. From here, we can come up with a few more hyperbolic identities pretty easily. So for example, if you were to divide both sides by cosh squared of t, then you can come up with this new identity which relates hyperbolic secant and tan. I suggest pausing here to check this division for yourself, but what you'll notice about this identity is that it's very similar to another trig identity that we know from high school. So here's yet another reason why hyperbolic functions are named after trig functions. Do you remember how I mentioned once before that the derivatives and antiderivatives of secant and tan always seem to be related? Well, the reason for that is precisely because of this identity which I just put there. So given that a similar identity exists for hyperbolic functions, we can expect the derivatives of sech and tan should be related similarly to how the derivatives of sec and tan are related. And we'll see soon that this is actually true. Also, if you looked at our original identity and divided it by sinh squared of t rather than cosh squared of t, you would end up with another identity relating cosech and cotang. Pause and check it for yourself. And note too that this is similar to the another trig identity that we already know. And with this, hopefully you're seeing that hyperbolic functions might be just what we need in order to get integral formulas that are similar but ever so slightly different than the ones that we already know, which I mentioned at the start of the video is kind of our goal with these things. But we're not quite there yet, so for now I suggest putting all these definitions and identities on your formula sheet, and we'll continue the discussion in the next video.